What I'm going to cover this morning is a little bit about the background to the project, particularly Drax history in developing expertise in the biomass area, an overview of the project itself, and looking from first principles, if you like, at the challenges that the project that we faced in delivering the project, and then to give you some idea of how we've addressed the solutions, and I'll make some concluding remarks. Later on this afternoon, John Pethulis from Shepherds is going to give a more detailed presentation of some of the technical detail behind some of the issues that I will raise this morning. So we've made sure that there's no duplication between the two presentations. So this will give you a taste for the justification of the project, the challenges that we faced, and how we've attacked them. So, a little bit about Drax as background. I started in 2005 because that's broadly when we really started the biomass journey. For those of you who don't know, Drax has got 6 operating units. They're all 670 megawatt units, which makes it about 4,000 megawatts in total, which is twice the size of the next largest power station in the UK. So it is a large operation. In 2005, that was about 5% of UK's installed capacity. But because the station is competitive and efficient, it actually produces between 7 and even sometimes 8% of UK power. When all the units are burning coal, it burns 10, sometimes 11 million tonnes a year of coal, which in the winter is 250,000 tonnes a week. And the CO2 emissions are between 22 and 24 million tonnes a year. And in 2005, that put Drax in the top 5 CO2 emitters in Europe. So as mentioned in the introduction, we floated the business in 2005, so we had to have a plan about what we're going to do with CO2 when you've got a problem that big. So we developed a business case for decarbonisation, and it really came down to a 3-phase strategy to deliver progressive reductions. The first was to improve the efficiency of the operation as best we could. The second was to progressively switch to renewable biomass from coal. And the third was to explore the potential for carbon capture and storage. And the plan was deliberately simple, and that plan largely remains intact today, 8 years on. We've done a lot of work to upgrade the power station. We've upgraded all the turbines, spent over £100 million upgrading all the turbines on the power station. We've upgraded the feed system and many of our drives, and we've had a 5% reduction in CO2 emissions just by making the plant more efficient. We then went on a journey to substitute coal for biomass, and as at today we've completed 2 of the 6 units, and we'll do a 3rd unit next year. So 33% of the station now has been completely substituted away from coal. And the final piece, which at the time we thought was a long shot, but as every month goes by, we're in more danger of actually having to do this project. It's the White Road project for CCS. We're now under FEED development with the government. This, if it comes to fruition, is a £1.8 billion project which will build a brand new power station at Drax, together with a transportation system which will take the CO2 to the shore just south of Bridlington and then store it 50 miles offshore in a sandstone aquifer. So that project's being developed now. We're about halfway through that FEED process. So broadly speaking, that was our approach to trying to reduce carbon emissions, and we've had quite a lot of success. What I'll focus on today is the biomass piece of this. So this chart, I won't go through it in too much detail, but I think many of you will have the same experience. We've just done a project, people are very interested in the project, but actually it's not just the project that has informed our decision making, it's 10 years of learning before it that have helped Drax get to where it is. We really started in 2003, but you can see the small amounts of biomass burnt. In fact, even in the first 5 years, we were burning not much more than up to 250,000 tonnes a year. And in fact, this chart goes up to April 2013, where we burnt a total of 4 million tonnes in 10 years. By the time we finish 2014, we'll have burnt almost exactly that amount in 1 year, which shows how much this has increased as our experience has gained. So we've learned an awful lot over a long period of time. This is a picture of the co-firing project which we did in 2010. To context it, this enabled us to co-fire 15% of biomass on each of our 6 units. In total we could burn about 1.5 million tonnes. But you can see we've got six storage units there, and in total there's 25,000 tonnes of biomass storage on site. The 2 larger ones are for rail receipts, and the 4 smaller ones you can see are for road receipt facilities. And that project was successful, but we did learn an awful lot from it. So that's our experience on site prior to this project. In addition, Drax has also been involved in the supply chain. One thing about biomass is this is a relatively new business. There's very few people we can go to who've got a lot of expertise in this area. We're having to go to different people with different expertises in different industries, apply it to our own knowledge, and then build up a larger project expertise. What this chart shows here is how we've also gone upstream to develop our expertise. What it shows is the supply chain from the forest through harvesting, processing, port storage, ocean freight, port storage again, and then rail to Drax. And some of you may be aware that we are in the process of building 2 pellet plants in the US at the moment. In fact, we're commissioning one now. We've built a port facility in the US at Baton Rouge, and we've also collaborated with 3 ports in the UK to put in port facilities. And our expertise is a mixture of doing it ourselves and engaging in long-term collaboration agreements and contracts in this area. And we've learnt a lot from getting involved in all aspects of the business. So this is a summary of the project at relatively high level. The capital cost of the actual storage and handling is about 170 million. That gives us 3 unit capability. There's also the fuel distribution system, which is another 70 million. So in total, receiving the biomass, handling it and delivering it to the boilers, we spent nearly 250 million pounds, and the capital cost for each boiler conversion is about 15 million. So in total, we spent 285 million in the conversion process. The project is, you can see, laid out there fairly simply. We've got brand new rail receipt facilities, and we upgraded our entire rail network on site to do that. That was 8 kilometres of track. We've got a screening building which screens using magnetic separation and gravity separation. We've got then the 4 domes for storage, 75 to 80,000 tonnes for each dome. And we've got then the retrieval facility taking it to our fuel distribution system. The rail loading and storage is all done by conveyor because of the capacity. The fuel distribution system effectively samples it, delivers it into day silos, where it then transfers to a pneumatic system for dust management, and from the pneumatic system it's then delivered to the boilers by pipe. And then it goes into the boiler, and we've had to do quite a lot of modifications. The capital cost looks small, which it is, but an awful lot of engineering time and effort's gone into making these changes not only effective, reliable and safe, but also improving the efficiency of the plant, because it's not designed for biomass, it's designed for coal. And the big difference, apart from the particle size, is coal is delivered often wet and biomass is dry, so the heat integration issues are significant. So that's the project in a nutshell. This is a bird's eye view, and you can compare actually what we've built for this Ecostore project to the original co-firing. See the coal stock there in front of you. Looking to the left, you'll see the 6 silos that we put in for co-firing, 25,000 tonnes of capacity. On the right, you'll see the 4 domes. You can also see the rail receipt facilities, that white building on the railway track, and then the conveyors moving it to the main boiler house. You can see, if you look closely at the diagram. To context the size of it, that coal stock, typically we operated between 1.5 and 2 million tonnes of stock. It actually did peak at 3 million tonnes in 1984 in the miners' strike, but typically it's between 1.5 and 2 million tonnes. So it is a large area, and that's been very helpful for us in developing the biomass project. So let's just look at the conversion plan and how successful it's been. This is the plan of the entire 3-unit conversion. We're now sort of really 2/3, maybe 3/4 of the way through this. So we converted the first unit in April 2013. The second unit we converted in April this year, and next year, probably the middle of the summer, we'll convert the 3rd unit. So we've commissioned all the common systems, that's now in place, and we've converted 2 units. And the project has been a success. One of the challenges was, can we get can we get the same throughputs or high throughputs out of the plant, because we didn't want to lose that much capacity from changing from coal to biomass. The design basis was 590 megawatts. We've actually achieved 645, which is exactly the same as coal. The nameplate is 670, which is what it achieves, but when you take works power off, 645 is what you export. So the biomass units have actually met the coal units now. The full load efficiency, we assumed a 1% efficiency loss, and actually that's only 0.5% now. And we've also got some ideas how we can narrow that gap even more. So at 38.5%, our biomass units are more efficient than most of the coal units in the UK. The output envelope we've managed to retain. Drax units are very flexible. They can operate between 200 and 645 on coal, and we've managed to achieve that on biomass, which is a great success, and already the National Grid use our biomass units to balance the system. And the reliability, we're aiming to get within 2% of coal. Our units generally are first quartile performers in forced outage rate. We typically get between 2.5% and 6% losses on each unit, and the biomass units are within about 1% of coal at the moment, although it's still early days. And the plant response, this is how quickly you can increase load or decrease load. We tried to the design base to make it comparable to coal. It's actually 50% quicker because the fuel is dry, and if you need to put more load in quickly, then you can get fuel in very quickly through the mills. The boiler distribution system works very well, and we can get the fuel in very quickly. So actually they are very responsive units, which is a benefit that we did not anticipate. So overall the project has been a great success. One thing I would say to anyone that's an operator in here, we've only run Unit 2 now for 18 months. It'll take 4 years, a full outage cycle, before I'm really confident that everything is okay, because as I'm sure there's things going on in there that we don't know is going on. Unit 2 has a major outage next year, so we'll get a chance to get in and inspect it, but so far so good. So this chart shows the same layout that I described 2 charts earlier, but it characterises the challenges that we faced. The purple ones are the common challenges across the 3 sections of the project. You can see with this on rail unloading and storage, dust is a major issue. It's a dry fuel, that's different than coal. Fire control is a big issue for us. Self-heating, many of you will be aware that biomass does self-heat. If you get moisture into it, it really heats up quite quickly, so you have to be able to control that. And also tramp material. That challenge is the same as the one we have with coal, but in biomass, because of the processing equipment you get, it's more delicate than some of the coal equipment that we've got, so it's quite critical to us. For the fuel distribution system, airborne dust, fire control and dry fuel are consistent challenges. We also moved to a pneumatic system, so it's really controlling semi-dense phase flow of the biomass. It can be problematic, particularly as our pipe runs are different lengths, which causes quite a lot of work on how much air we need and what sort of pressures to operate at. And also gravimetric control is how we feed the units in a controlled fashion, and that not only has to work at steady state, but as I mentioned, because we follow load and respond to National Grid signals, that needs to be pretty flexible. And then on the combustion side, fire control again is a big issue in there, and then the rest of it is really to do with the boilers. I won't spend too much time on that, that's not the focus of today, but I'll touch on it briefly later. But we had to modify our coal mills. The speed of combustion was an issue. Heat integration, I mentioned, was a big challenge for us. Flame stability, would biomass burn in the boiler in a stable flame, and could we then detect it to make sure that we didn't get a flame out situation, and then fouling and corrosion. So those are the challenges that we faced, and we'd seen them all to a greater or lesser extent over the previous 10 years, but to move from a 1.5 million tonne project to a project that's going to deliver between 7.5 and 10 million is a different order of magnitude of challenge. The next 2 charts just briefly look at some of the hazards. Some of them were mentioned early on at the early presentation, but creeping fires on horizontal ledges is a characteristic of biomass operations. If you don't control the dust, it builds up on ledges and horizontal surfaces, and then if you're not careful, you will get fires. The one on the right is the remnants of what was a storage fire actually in one of the rail silos we had. So storage fires and self-heating is an issue. When we went down this road, almost every operator we spoke to, either in Scandinavia or mainland Europe, said if you're in the biomass business, it's not if you'll get fires, it's when. And if you're going to have fires, you've got to be organised to be able to cope with it. And then the other area is dust. On the left you'll see a motor. If you're not careful, dust does get everywhere. You really have to get religion about managing dust if you're handling biomass. On the right hand side we did some test work originally to see whether we could use biomass in our existing coal bunkers. And we brought in a couple of vendors to show what their chutes could do in terms of dust mitigation. This is one of the efforts. My team sat down, watched the video, and within 5 minutes we just couldn't contain ourselves. We spent the whole morning laughing about it, and we decided we can't use coal bunkers. You just can't do it. So that's why we used a pneumatic system. But simple practical tests showed that what was possible and what was not possible. So, a little bit more detail. For us, biomass to coal is not just a fuel switch, but it can. So you've got to treat this very seriously. You can handle it safely if you use systems that really focus on what are the risks. So biomass, low density, must be kept dry. Transport and storage must be designed accordingly. I'll show you later one of our rail wagons. The rail wagons is there to handle the density. Clearly we've put the domes in place. All the rail wagons have got roofs on. None of that was in place with our coal operation. Eliminate airborne dust at every opportunity. We've done this, really attacked it from every angle. So we've really worked the fuel specification. We actually worked the fuel specification on the pellets to change them to try and minimise the amount of dust. We've modified our conveyors and the transfer points, and also our rail receipt facilities to again minimise dust. We've also extracted dust at every opportunity and not put it straight back onto the biomass. When we extract the dust, we then take it straight to the pneumatic system. So at every stage of the system we extract dust and don't put it back in, which really helps the process. That was new for this project. We'd never done it before, and it works really well. And also isolate wherever possible. All our conveyor belts are enclosed, but they're also easy to clean, and our pneumatic systems just keep it trapped inside the pipe. So for us, we didn't want any dust in the boiler house at all because of explosion, potential hazards and fire, so the pneumatic system was the obvious solution. The bulk storage needed careful management. It's been quite innovative what we've done at Drax. We've tried to target zero retained material, so the fact the domes have got vibrating floors on them, so we can fully empty the inventory. No biomass stays in there over time, so we fully cycle the domes to empty them for all the material. We also have temperature control and good gas monitoring in there, and we inert the biomass when it's stored with nitrogen, and we've also got the ability to box in the domes, increase the nitrogen content, and also flood it with CO2 from the head house, which we have not had to deploy the CO2 at this stage, but the nitrogen blanketing really works well. And the fire systems, we had to be innovative. You have to be careful. When you get biomass wet, it swells to 3 times the size and it's not usable. So you've got to be careful where you use sprinkler and deluge systems, and you've got to use proven detection technology. So it's different detecting fire or even smouldering when it's in chutes, when it's on conveyors, and when it's in domes. So you have to be very careful about targeting how you detect fire and then how you attack it. On the combustion side, won't spend too much time on this, but chemistry is key, and that's back to the fuel specification. We also add a mitigant to the biomass in our boilers to try and reduce the effect of fouling. The heat integration, I briefly mentioned earlier. We did a project to take heat out of the coal mills to try and reduce the temperature in the mills, which we achieved well, so the biomass didn't just combust within the mills, and then use that heat for change the feed water heating system, and we saved about 1% of the energy loss by doing that modification. The milling plant we had to modify. Coal is a friable substance, biomass is bouncy and resilient, so how do you solve that problem? And that's really getting the pellet specification right, the particle size right. All we really do at Drax is break those pellets up. All the milling is done off-site where you produce the pellets in the first place. and this pellet specification was critical to that, but also the residence time in the boiler. Every now and again you need a lucky break. Drax boilers are very big because Selby coal was so poor quality and caused a lot of fouling. Our boilers are large. Because the boilers are large, we have got more residence time than most other coal units, and that helps the biomass burn in time before it goes out the back end. So speed of combustion is critical to us. And then finally, flame stability. We've had to modify all our burners. So just a couple of examples of the chutes. We've on the conveyors, we've used this Tunra chute design. This is an Australian vendor. This was designed for the minerals and mining industry, really to reduce wear and tear on conveyors and also minimise dust. It seemed the ideal design from us from our own experiences, and what it does is it sculptures the flow of biomass from one conveyor to another, really minimises the shock loading, and it reduces the dust production significantly. We've been very pleased with that technology. If we look at dust, we tried to minimise flat horizontal surfaces wherever possible. You can see these are simply polystyrene cones, almost like Toblerones, that we put on top of girders so that dust can't gather on the girders. A very simple modification. People always remark on it when they see it. It does look unusual, but it works. Dust does not settle on horizontal surfaces. All our buildings, we don't leave building internals exposed. We cover them up, so they have clean surfaces so the dust doesn't stick on it, and all the cable trays are made of wire. There are no solid trays again, so dust doesn't gather anywhere. Fire detection. We use infrared technology, which won't surprise you, but we use different technology for our conveyors, looking at solid beds, which then trigger our fire systems. But on the chutes, we use a firefly system where it detects any fire and then is extinguished immediately with a water mist. This works really well, and so far we, in handling best part 4, well no, now nearly 6 million tonnes have gone through the system. We haven't really had a single fire problem at all. The dome inerting, this has been a real success, and I'm sure John will talk about this afternoon. On the right we've got just a diagram of the nitrogen system. Basically the nitrogen feeds up through the floor. We fill the dome with 20% biomass, and then we flood it with nitrogen. It flows between 1,200 and 3,000 metres cubed an hour and takes about 24 hours plus to get the oxygen levels down to negligible amounts. We use 93% pure nitrogen, so it's in industrial grade. This works well. Since we've done this, we don't get any temperature. As soon as you inert the dome, we don't get any temperature deviations in the biomass at all. It keeps the temperature absolutely rock steady, which compared to our other facilities is a different world. So this has worked very nicely for us, and is probably one of the major successes of the project. We've also got CO2 facilities in the head houses of the domes to deploy should we get into a fire situation. This just shows a couple of pictures of things that I've talked about. So obviously the dome's top left. Top right is the inside of a dome. It's a W profile floor. There are 2 conveyors running in parallel at the bottom of each of the W's, and you can see on there the vibrating floor panels, which we only operate as we come to empty the bottom of the dome out. Without the vibrating floors, there'd be about 15% of biomass left in the dome. With the vibrating panels, we can empty it almost completely before we then refill it, and that's the cycle that we use. Bottom left is the nitrogen system, which basically uses basic sieve technology. Nothing unusual about that, but it's relatively low cost and works well. And bottom right, that's the rail receipt facility. So you can see the clean lines of the building, all internally covered up. No horizontal areas for dust to catch. But even though we've over-designed, if you like, the inside of the rail receipt facility, the actual dust that we get when we offload the trains is actually very small. We've put Burnley baffles in under the rail unloading, and it works well. Train takes about half an hour to offload, 25 wagons, and the system works nicely. The next area really was the transfer from conveying technology to pneumatic conveyancing, which was new for Drax. We haven't got much with this, and this is basically a three-stage airlock system. Again, quite commonly used, not unique in any way. It's just the scale of it at Drax. We've used a shank system. It works well. You can see the air blower at the bottom, the airlock system on the left. The transportation lines, they vary from between 100 metres to 300 metres in length, so there's quite a big difference in performance. In fact, we need different size blowers to handle the different runs. And at the other end, again, you've got a rotary valve which separates the pneumatic system from feeding the biomass straight into the modified coal mills. So it's a very simple process. We have 10 mills on each unit, so we have 10 separate systems for each unit. So for 3 units, we've got 30 systems like this, all built in a tower. In fact, the next diagram shows this. So these are the dome valves underneath the feed hoppers. You can think there's 5 or 6 of them there. And on the left-hand side, you can see the pipes feeding from the biomass distribution tower towards the units. This is the back of the boiler tower. You can see the electrostatic precipitators on the left-hand side. So this goes on the outside of the boiler and goes in. Some practical solutions here mean having the pipes outside means the fire risk reduces, dust risk reduces. We've also got the ability to get access to all these lines every 25 metres. So if a pipe blocks, we can get in there and unblock it very quickly. So we can manually open these pipes every 25 metres, which is a very practical solution. And during commissioning, that was helpful. And as we optimise the blowers and try to reduce power consumption, every now and again they block up. So to get access to be able to unblock them easily is very helpful. This picture shows this is the 2 big hoppers you can see in the middle. This is where the conveyor system drops into 2 main day silos, and then it drops into the pneumatic system, which I've talked about with the shank airlocks. So that's what it looks like before it goes into the boiler house, which is that big building on the right. And on the right there is our new rail wagon. This is a first for Drax. This is a Drax patented rail wagon. We did this because coal wagons are designed for basically a high density material, and we couldn't really make effective use of them for biomass. We did use rail wagons for quite a few years, but modifying this wagon means we get 30% more biomass in each wagon. We've now commissioned 8 sets of 25, of which 5 sets have been delivered. They work nicely, so we got a 30% increase in volume, and going from 22 rail cars for coal to 25 for biomass, and the 30% increase means now a biomass train almost carries the same weight as a coal train, which has really reduced, A, it reduces our costs, but B, it reduces the carbon footprint of transporting fuel. And these rail wagons have worked pretty well. 1 or 2 teething problems, but by and large, that's been a success story. This it looks at 1 or 2 of the construction challenges. For us, we're not used to big civils projects. Most of ours are structural and mechanical jobs. The domes, each one is 8,000 tonnes of concrete. We had a concrete facility built on site. Each one took 26 weeks. What's interesting about the domes is you put the skin on first and then you build it from the inside, which actually is very helpful in terms of construction work during the winter, because it takes out the element of weather on schedule. So that worked well for us. And on the right, the rail system, this was a real headache because we're taking 15, 20, 25 trains a day just to keep Drax running, and we needed to manage our stocks and take the rail system out. We replaced 8 kilometres of track in 22 days, and we did that because we're having to increase the speed of the rail deliveries from 5 miles an hour to 15 to get the volume of product through with a mixture of coal and biomass, and that job went very well indeed, and you can see it now. It's a state where there's no rail tracks, so that was a bit of a worrying period during the summer of 2013. Okay. So just to conclude, the project is really the culmination of 10 years' work. A lot of work we've had a very committed group of engineers at Drax working on biomass throughout that period, and they've come up with quite a lot of innovative solutions. We've also had, as you can imagine, an awful lot of people telling us what we should be doing, and a lot of it has been based on very little experience. So we've used third-party expertise, but we've applied it with caution. one of our guiding principles is that as a business we try to keep certain core competencies in-house, and I think this has paid off for us. When we went with Shepherds for this project, we were very careful in the selection of our construction partner. We wanted somebody that would collaborate and learn with us, and that has gone well. And I'd like to thank John and his team for all that they've done for us. And I think the focused effort has delivered results. The project's largely successful. We've done two plants. The design basis has been met, and the third one will be done next year. But I think the important thing to say is that lessons still remain. We have achieved a step change in dust management, but regular intervention is required now and again, particularly if we get a very dusty cargo. People don't always stick to the spec, which is something else we're working on. So you have to be on your guard. We've also identified several improvement opportunities already, and full throughputs will be achieved by the end of next year. So we aren't quite there yet. We're 2/3 of the way through the project. And I think the final point is really never get complacent about handling biomass. I think the key thing we try to do is learn lessons quickly and apply them, and try to get into everybody's heads on site that actually we need to be really chronically uneasy about this operation. We need to be checking it all the time and making sure that everything is running as it should do. That's it.
Thank you very much.